method, and this was actually advanced problem of the homework you're turning in today. So let me show you the phrase again. Why does Newton's method work? That's what I'm about to explain. The beginning part was discussed already, so I'm just repeating here. Suppose our f of x is simple over AP, over the interval AB. So for example, concave up, it does not change the concavity over there and is always increasing. And it crosses x-axis in between A and B. So that's one of the picture I showed you. Then if you start within the middle, x0, and using the picture I was trying to explain, that next number, next iterate in the Newton's method is to the left. This C is a typo here. It's supposed to be alpha. Where it crosses, it is trapped in between. It keeps going to the left. It never goes to the left of C, or alpha, I'm sorry. So from there, I concluded that that number must approach somewhere. Not necessarily alpha. For example, to you, it is to your left. The numbers keep going to the left. Never exceed this number. It must converge to something. You can't just wander around and behave complicated. It must converge to B. So that's monotone sequence theorem. You learned a better statement in the Calc 2. Still, they don't prove it. It's very fundamental part. It's difficult to actually prove it. You end up with a lot of circular reasoning. Alright, so that part we accepted. Xn is going somewhere, and we want to show why that point that is going is actually alpha, which is where it crosses. So I'm going to copy this and explain to you. So here's the situation. Here's the where alpha is. This is where function crosses like that. And information we have here, we started at x0. The Newton's method will take you here and there. Keep going to the left. So we assume that this seems like this one approaches beta as we keep doing this Newton's iterate. And this is asking, can you actually logically explain why where this one is going is exactly alpha? Alright? That's what I'm about to explain. So here is a proof. These xn's are Newton's method, obtained from Newton's method. So I'm going to write down the Newton's method. Xn plus 1 is xn, right? Remember the rest of the part? What is Newton's method here? Minus, right? What's in the numerator? F of xn divided by f prime of xn. So you start here, you have f of x, you calculate f prime, keep doing that, and you get to the answer, right? So what we have assumed here is limit n approaches infinity of xn. This exists, right? If you keep doing that forever, it's going somewhere. So we denoted this convergent limit of this sequence with which letter? What's that? Beta. That's right. That's beta. All right. Here's a tricky question. Xn approaches infinity. What do you think is going to happen to x subscript n plus 1? Which letter is it going this time? Alpha? Beta plus 1? Alpha? Anything else? What if xn was 1 over n? Where does that go? 0. How about xn plus 1, which is 1 over n plus 1, right? Where does that go? 0, right? How about xn plus 2, 1 over n plus 2, where does that go? 2 over 1 over 2? Or is this not correct answer? So what happened to that one? Goes to 1? How about this one? 1/2? Fair enough? Why does that go to 1? N is not approaching because n is infinity, remember? Yeah. So what happened to 1 over n plus 1? 1 is not correct answer, right? Where does that go? It's 0. Correct. How about this one? 0. 0, right? They're all going the same. So where does that go? Not 0. In this case. Here it's 0 is correct. What about here? Most logical conclusion here? It's beta again. If xn is going to beta, what could happen to the one that above, ahead of that goes the same place? All right. So let's look at it. Left hand side is going somewhere, right? Right hand side, this is going somewhere, correct? And f of xn is going somewhere. So how about limit s approaches n approaches infinity f of xn? And we want to put that limit inside f of n, right? F of x, right? And I claim we can do that. You can just bring that limit operator inside there like that. Which property of f allows you to do that? Since f is what kind of function? Continuous function. Thank you. If you look up, going back to session 1, the very definition of continuity, this is exactly continuity. What is happening when you play with inside the input is exactly what you expect in the output. Alright? So this one, what happened to xn? That xn approaches beta, right? So that one converges as well. How about that one in the denominator? Limit n approaches infinity, f prime of xn. Can I bring that inside there? Like that? Since f prime is continuous. This is about f prime, and that's why I had to assume that f prime is continuous. Is continuous. Most functions, polynomial, exponential, those elementary functions have this property. Alright, everything here converges, right? Is going somewhere. Especially f prime of xn. This one goes to f prime of, this whole thing goes to beta, right? If that one goes to 0, we can't apply BLP in here, right? This is in the denominator. Can someone explain why this one is not going to 0, not going to be 0, so that we can easily apply BLP? Let me show you the earlier condition. These are the complicated context, make things simple, right? Our calculation simple. In which other condition do you think it guarantees that f prime of beta is not going to be 0? But looking at here, there are lots of conditions here. F prime is what kind of condition? Concave up or increasing, decreasing? F prime is an increasing, decreasing, correct. So what does it say? Increasing, right? So what kind of f prime value are we looking at here? Always positive. Increasing function is increasing, f prime is positive. Remember that? F double prime is positive. F is concave up. Therefore, you conclude here, this is going to be positive, never 0, right? Since, what's the correct f is, what kind of function? Continuous is not the answer. F increasing function, that's right. Increasing function. Alright? So, the point is that everything involved in here converges to something, right? And even the denominator converges to non-zero number. Everything's good. So I'm going to apply limit operator to left-hand side, xn plus 1, right-hand side like that, but you can apply anywhere because everything is good here. And this distributing limit everywhere, do you know what this one is called? If I have to tag in over here, what are you going to tag over here? Why can you do that? BLP is correct answer. Yeah, that's, if you think about it, that's exactly BLP. Alright? And one thing that we have to check is the denominator, right? So let's pass to the next level. What is this limit of xn plus 1? Xn plus 1? It's a letter. That was beta. How about this one in here? If this one goes to beta, and what happened to that guy? Went to beta as well. Minus what happened to that? So I forgot to write it down. The whole thing is inside. It's down there. Inside is beta, right? Xn approaching to beta, so it's f of beta. Okay, so inside is beta, so you go in there if beta. How about this one? F prime of beta. So if this is always true, limit must be true because everything limit exists. So you have to pass through that. This is a silly equation, isn't it? Beta and beta, they cancel, right? So what do you have? Beta, f of beta divided by f prime of beta is equal to 0. Beta and beta additively cancel. Okay? So in what situation you have quotient that is well defined, it happened to be 0. Numerator 0, denominator 0. Numerator must be 0 and denominator must be non-zero, so that is defined and 0. Right? So what we have just proved here is that the number that Newton's method generates, that number beta, if you plug that number into the function, it's becoming 0. So the conclusion, we have one number, f alpha, that was 0. That's the beginning context in here. At the beginning, we assume there is this number such that it's a 0. And this Newton's method gave gave a different description of number such that it's a 0. And we want to conclude alpha and beta is equal to each other, right? So I'm going to show you one more time this context in here. Which part do you think it guarantees that this alpha and beta must be equal to each other? Function definitely can have two zeros, right? There are many examples of functions that have 2 zeros and 3 zeros and short interval, right? So how do you know this alpha and beta we got is actually equal to each other? We assume this f of x is not going up and down. It's a pretty simple shape, right? So there are two conditions, concave up and increasing. Which one do you think is responsible for concluding logically that alpha must be equal to that beta from the Newton's method in this one here? Concave up? Does that make sense? Why is it concave up? What is greater than 0? F double prime, right? So I don't see the connection. How about increasing? You cross once alpha, right? Once alpha, it just keeps increasing. It'll never come back. It'll never come back down and hit 0 again, ever, right? What about before alpha? If it's increasing, it must be down there before it hits 0. Increasing guarantees that if it hits x-intercept, if it hits x-axis, it hits at most one time. You cannot hit 2 times. That means come up and down. And you can use Rolle's theorem to show that. So let me conclude it that way. We can conclude that alpha equals beta because since f is what kind of function? Increasing function. If these two things are different, you hit alpha once and beta again. That means you have to come up and down and do something in between. By Rolle's theorem, in between there must be derivative 0, but derivative is always positive. Right? That's a rather rigorous proof. Alright, so that's why it works. Make sense? This is Latin abbreviation QED. I don't know what that really is, but it means the end of proof. Alright. Right? It's not much you did. You just very simple argument, and we didn't do anything about f prime, right? If you have anything that looks like sig, you keep iterating. If there's f of xn, and then you can do something else. As long as you can conclude if they converge, this argument seems like following all the time. They must go to the same zero. It's a strange argument. So there are actually slight tweaks of this method so that you change the denominator a little bit so it improves the, it goes to 0 a lot faster and things like that. But this is actually tricky to pull out. Actually, xn converges. That's not easy to conclude. All right. Does this proof make sense? Okay. Right. Right. So let's just stick to this one. And any question? All right. Let me know later if you found some question to ask. So that's why it works, and sometimes it doesn't work. When does it not work? When you're not looking at concave open increasing or the mixture, and then it sometimes doesn't work. So let me show you the picture. I think it's really fun to understand this. Here's a y equals sine x. You see 1 alpha there, right? You see alpha? What's that? Right? Right. It's mixed, right? Over this interval mixed. Here's our 0. We want to have around that x 0 where it's always concave up, always concave down, right? Then Newton's method is guaranteed to work. However, I can't do that. To the right, concave down, to the left, concave up, right? So I'm going to show you some extreme behavior of what happens if it's mixed up like this. Can you imagine somewhere here, I apply Newton's method, you go up, right? And then you draw tangent line, you end up at there. But that number is the exactly opposite side amount, like symmetric. Then you go there, exactly same picture is happening, right? You landed in exactly where you start. Do you see that? Go up, you go here, and draw a tangent line, you end up at exactly the way you started. And then you never get anywhere. And here's the number that I calculated. If you started at 1.16556118520, I will give you a better description of this number. It's approximation. You go up there, tangent line landed in here, and from there you x1, calculate x2, x3 here, x4. They're not going anywhere, just trapped in there forever, right? So what's going to happen in Newton's work? Does it work? Does it not work? It doesn't work. It's not going there, right? If you actually choose a small number in here, is wander around, eventually, but very slowly, goes there. If it is good shape, it actually goes really fast, and in this case, it's a very bad case. So how can things like this happen? So let's think about it. In this case, I start here as x0, right? Then you get to x1, then x0 minus, what is up there? Sine x0. Does that make sense? That's what f of x0 is. F prime of x0, cosine x0, right? And this thing is x1. And I was saying that if it is exactly opposite side, I'm sure because of the symmetry it's going to come back. So what is this one? Negative x0. You see that? I assume that next one is actually negative x0. So if I move this over here, it's a 2x0 minus, what's a better name of this guy? Tangent x0. Oh, is there any number such that 2x minus tangent x0 equals 0? If you calculate it, using what method do we have to use to solve this type of equation? Bisection method? And 2 days ago, we learned Newton's method. You can apply Newton's method again just to find this weird initial value. It's very confusing. But suppose there is this one, x0 right there. That number is 1.1655 and so. So if you started here, you're trapped in here forever. All right? So I gave you two numbers. If you start in two numbers, you're not going to get anywhere. And here's a more interesting situation. Do you see that there are many of that boxes down there, right? So this is the one that we just looked at. So if you started here, you get nowhere out of Newton's method. If you started there, you get nowhere from Newton's method. And there are many, many more in here, right? So I'm going to show you a more interesting one. So I'm going to start from here, draw a tangent line down there. Does it look like a tangent line? And if I start from there, down there, this value, if I start from that value, that's your point, and tangent line hits where? It hits there, right? Now from there you're trapped. You see that? x0, x1, x2, x3, x4, x5, x6. Not going anywhere. Alright, so let me give you another one. How about that? There. If I start from that x0, you started there, you landed in there. x1, x2, x3, x4, trapped forever, right? You can keep drawing this lines forever. There's another one. If you started there, boom, go there and trapped in there, right? And you can, just one point, you can stretch the forever to the infinitely many points apart. Here's even more strange part is that you can even start from in here. You can, okay, that's not trapped in it, eventually trapped, right? So how can I land it in here? You can go all the way, for example, there. If I start from there, x0, tangent line go, you landed in there, right? That's x1. Now that's x2, x3, x4, x5, x6. Now you're trapped, right? Then you can put this number everywhere densely. It's so confusing, such that if you started with the somewhere x0, you landed all the way over there, but right next to a millionth unit to the right, and you landed over there. This is very, very chaotic, and you depending on your initial value. This is sometimes called butterfly effect. It's small amount to your initial setting result in a completely different outcome, right? It's sometimes called chaotic theory in mathematics and things like that. So initial value, if it is not concave up and increasing like that, if it is changed a lot, what Newton's method is doing is very difficult to understand. So they measured it, and how much it's going to be difficult. So for example, they created this type of picture. This is degree 3 polynomial. If you start it, and to get a complete picture in mathematics, often you have to go to a complex plane. And that happened to be true in physics as well. If you enter physics, you have to deal with complex numbers. That's a full picture that we don't see. So if you go to complex number, if you started here and do the Newton's method, you converge. If you started there, you converge. So these are the good area. Newton's method behaved nicely. But there is this region in between. There's infinitesimal complexity in there. If you start from there, it wanders around and going nowhere. So this picture is kind of showing that how complicated this problem is. And this set I just showed you is called Julia set. Collection of all initial value that eventually create chaos, or wandering around and not going anywhere under this type of Newton's method. Right? This became a very, very interesting problem. Many mathematicians spend a lot of time on this to understand this one. On top of this Julia set, next level is something called Mandelbrot set. You can look that up, and that's very, very famous set. You've probably seen this picture somewhere. All right, keep going. That's how it doesn't work. Also, I told you that this Newton's method is so good. If you have 4 digits correct, if you do one more, you get 8 digits correct. If you do one more, you have 16 digits correct. And that phenomenon is just amazing. So I'd like to explain that very quickly because it's very easy to explain. And here is a formula you have seen before. What is this? Quadratic approximation, right? Approximation, that's why there's this symbol right there, right? Not equal. But you're going to see that changes to equal symbol. And what else changed? Inside value in here, right? Accent, it's not accent, it's an accented accent tilde. Just like a mean value theorem. Remember, the secant slope of the secant line is equal to Mr's value inside f prime equal to. So there is some choice of value in there that makes these two things equal. So these two things are equal to each other. And this xn is actually in between your this where the quadratic approximation is calculated versus your input value. If the function is quadratic, and this quadratic function, this gets actually really simple. So that's why I'm going to explain it. So let's take that formula, which is almost the same. You already know this formula very well. You've practiced a lot. One difference is that this changes the equal symbol, and last value is xn tilde. Right? So here's what we're going to do. We're going to just assume f of x is x squared minus 2. Then you know what we're computing, right? Newton's method will give you what number? Square root of 2, right? This one set equal to 0 gives you square root of 2. Make sense? The 0 of this one is square root. Newton's method will calculate this 0 square root of 2. We did that Wednesday. All right, so f of x and is equal to, you can actually replace that one in there, but I'm just going to do it like this. It's more fun. Xn is that nth iterate in Newton's method, and you know what f prime of xn is. You can use this one to calculate, and x minus xn plus f double prime of xn tilde. Well, we don't know what that is, somewhere in between. That makes it equal to an x minus xn squared, right? The next trig is very difficult to see, but see what happened. What if I plug in square root 2 in there, right? Square root 2 and square root 2 in there and square root 2 in there, right? So is the square root 2, what happened if I plug in square root 2 into f of x? 0, right? So left hand side becomes 0. Right hand side, I'm just going to keep it that way, f of xn minus f of x and as square root 2 minus xn plus f double prime of xn tilde divided by square root of 2 minus xn. Right? So since it's a 0, I'm going to move this one over there, negative f of xn, and divide by this coefficient, which is positive. Am I doing this right? Negative is a positive, right? Positive f prime of xn. Then I subtracted this one and divided by this. What's left is the square root of 2 minus xn. And minus, I divided by this one, so I put f prime of xn tilde. 2 times f prime of xn down there, and square root of 2 xn. This is what we got. I'm going to move this thing to the other side. Do you see that there's xn plus, I think I copied this one only, that's why it went right. This is supposed to be positive. Remember when you're writing down as a positive? So when you're dividing, you still keep this negative here, and that's positive. All right, divided that, it's positive. Then, if you move that one over there, it's xn minus f of xn divided by f prime of xn. If I subtract this one as well, negative square root of 2, right hand side now is f. What is f double prime of x if it is x squared minus 2 there? 2x, right? Not 2x, just a 2. So it's disappeared. It doesn't matter what that mysterious value is, it's just 2, right? So that's why I chose this example. What about this one? F prime of xn. Isn't that 2xn, the derivative, right? And the square root of 2 minus xn. Because of that. What is your question? Oh, squared. Thank you. Squared, squared, squared. All right, thank you. So, I want you to look at the left-hand side. Oh, I recognize that guy. Do something about left-hand side. What is it? What's going on in the left-hand side? So far, it was just quadratic approximation, right? But what happened left-hand side? Something you recognize, right? First two term. What is it? xn plus 1. So once you write that down, the magic just kicks in. xn plus 1, next iterate, minus root 2. That measures how close is the next iterate to square root 2, is equal to, this 2 cancel, and it's 1 over 2 times xn, times square root 2 minus xn. That nth iterate, how close it was, right? It's squared. So I'm going to compare that. This xn, we started usually from 2. After you do that is 1 point something. So these numbers are absolutely less than 1. This xn is close to 1. So you can safely say that by looking at the data that this is less than square root of 2 minus xn squared, because this guy is less than 1. Now this measures how close your xnth iterate is square root of 2. This measures, how about next one? How close is that now to the square root of 2, right? And it says the following. If this one has 4 decimal places correct, how is this number going to look like? 0.0000, right? 4 decimals are correct. If you subtract, you get zeros, right? Whatever that is after the rest of the side. What happened if you square that? You have a 10 to the negative 4, right? What happened if you square it? 10 to the negative 8. So if you square that whole thing, you're going to get 0.0000 and 0.0000. This number is going to be this small. And that number is even smaller than that. Therefore, this number must have at least 8 digits correct. And if we started this one again, then 8 digits, the next one is 16 digits. This next iterate will get 16 digits correct. This is really cute. How fast it's approaching. Right? By just doing it a couple times, and you get all the accuracy you need in entire physics problem. You need all the way down to probably 27 digits, and you don't need any more accuracy than that in any physics problem. All right. No, it's not substituted. This whole thing, remember, xn plus 1 in the Newton's method. That's right. Yeah. Anything else? Right, tilde, because it was a special example. So if you differentiate it